is Taylor Tumbleson. I'm a senior mathematics major at the University of Houston downtown, and my senior project is a graph theory problem about the independence and residue in trees. So the independence number of a graph, denoted alpha, is the cardinality of the largest independent subset of vertices of the graph. So if we look at the graph below, the vertices that are circled is going to be the largest independent subset of vertices, and the cardinality of this set is 8. So here the independence number is 8. The residue of a graph, denoted R, is the number of zeros left in the degree sequence after reducing it using the Havel-Hakimi process. So we're going to demonstrate that process using the graph below. So first we want to start by taking the degree sequence of the graph and putting it in descending order. Then we want to eliminate the maximum degree vertex, so in this case 5, and then subtract 1 from the next 5 vertices. Now what you're left with, you want to go ahead and reorder. In this case we don't really need to because they're already in descending order, and then repeat the process. So eliminate the max degree and subtract 1 from the next 2. So now I'm going to reorder this and then just repeat this process until we're left with all zeros. So the number of zeros left here is 6. So the residue of this graph is going to be 6. So we already know that for any graph, the residue is less than or equal to the independence number, but our goal is to show that the residue is strictly less than the independence number, except in trees specifically, except for in a few cases where the residue is actually equal to the independence. So a tree is a type of graph that contains no cycles like the one below, and the diameter of the graph, denoted delta, is going to be the greatest distance between any pair of vertices, where the distance between any pair of vertices is the length of the shortest path between the two vertices. So if we're looking at the graph below, the highlighted path is going to be the diameter, which is the length of this path is 7. Now we're going to let L be equal to the number of leaves of a tree. A leaf of a non-trivial tree is going to be a vertex with degree 1. So here is an example of a leaf. And any vertex that is not a leaf is called an interior vertex. So this is an interior vertex, as is this one, as are the rest of them that are not leaves. We wish to prove the following theorem. Let T be a tree with diameter greater than 6, then the residue is strictly less than the independence number. This result is an improvement over the residue less than or equal to independence, but our proof is independent of that proof. If we notice the sample graph that we had in the previous slides, our diameter is equal to 7, which is greater than 6, and the residue is equal to 6, which is indeed less than the independence number. So for this specific example, our theorem holds. So before we get started proving the main theorem, we want to address a couple of lemmas. So the first lemma is going to be fundamental to our main proof. It depends greatly on this lemma. So let D1 and D2 be degree sequences for graphs G1 and G2 respectively of the same order where D1 majorizes D2. Then the residue of G1 is greater than or equal to the residue of G2. So to give an example of what it means for one degree sequence to majorize the other, let's take into consideration these two degree sequences A and B. So when we're talking about majorization, we're looking at the partial sums. So in the first degree sequence A, the first partial sum is 8, and in the second degree sequence B, the first partial sum is 5. So we see that the first partial sum of A is greater than the first partial sum of B. And further, the second partial sum of A is 10, 8 plus 2, and the second partial sum of B is 5 plus 3, which is 8. So for these specific degree sequences, the partial sums of A are going to be greater than B up until the fourth partial sum, and then they're equal everywhere after that. And even further, if we take the degree sequences of both of, if we take the, we find the residue of both of these degree sequences, we're going to see that the residue of A is greater than the residue of B. So this is an example of this lemma holding true. For a second lemma, let T be a tree that is not a single edge. Then the independence number is greater than or equal to the number of leaves. So to show this, let's look at this graph on the right, and we want to choose a maximum independent set A that contains the maximum number of leaves. So in this case, the maximum independent set includes A, B, D, G, and X. So it contains all the leaves and then also this vertex D. Now suppose every leaf is contained in A, then alpha is greater than or equal to L. So here the cardinality of the maximum independent set is 5 and the number of leaves is 4. So the independence number is greater than or equal to L. Now if every leaf is not contained in A, then suppose X is a leaf and X is not in A. Then X must have a neighbor Y that is not a leaf. But because X is not in A and A is the maximum independent set, then Y must be in A, because otherwise the union of A and X would be larger than the independent set A, which is a contradiction. Finally, we want to create a new maximum independent set A prime that consists of X and A where Y is not in A. Then A prime is a maximum independent set with more leaves than A because it includes X, which is a contradiction. So it follows that A must contain all of the leaves. Thus, the independence number is greater than or equal to the number of leaves. For some definitions, we're going to go ahead and look at this tree. The degree sequence of this tree is going to be as follows. And J1 is going to be the number of vertices of T where the degree is greater than or equal to 3. So in this case, 4, 4, and 3. And this is excluding the maximum degree vertex. Moreover, let J2 be the number of vertices of T with degree equal to 2. So here there's 5 of them. And then K is going to be the sum from 1 to J1 of the degrees minus 2. So in this case, we're going to take 4, 4, and 3, we're going to subtract 2 and add them together, and in this case, K is going to be equal to 5. Next, let T be a tree and let D be the maximum degree of T. Then the number of leaves is equal to D plus K. So this lemma was proven using a depth-first algorithm. It's fundamental to the proof of our main theorem. It's kind of a long algorithm, so I'm just going to kind of give an example of this being true. So if we look at this graph and its degree sequence, we can see by inspection that the number of leaves is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's easy to see by just looking at it, but we can also show that it's true that in this example, the maximum degree is 6 and K is 5, which we showed in the previous slide. So it follows that D plus K is equal to 11, and the number of leaves is equal to D plus K in this example. So now for our main theorem, let T be a tree with the diameter greater than 6, then the residue is strictly less than the independence. The proof of this theorem has been broken up into 3 cases, and each case depends on the fundamental result shown in lemma 3, namely that the number of leaves is equal to D plus K. So the 3 cases are as follows. Case 1 is where D plus K is equal to J1 plus J2. Case 2 is where D plus K is greater than J1 plus J2. And case 3 is where D plus K is less than J1 plus J2. So we do want to recall what J1 and J2 are. J1 is, again, the number of vertices of T with degree greater than or equal to 3, excluding the maximum degree vertex. And J2 is the number of vertices of T with degree 2. So the proof of case 1 consists of 2 lemmas. The first being, if d plus k is equal to j1 plus j2, then there must be an interior vertex that is not adjacent to a leaf. So by way of contradiction, we want to suppose that every interior vertex has a leaf adjacent to it. Thus, the number of leaves is greater than or equal to j1 plus j2 plus 1, since j1 plus j2 is the amount of interior vertices, and then the plus 1 because we have to consider the maximum degree vertex. However, d plus k is equal to j1, j2, and since L is equal to j1 plus j2 and d plus k is equal to L, this is a contradiction. Thus, there is an interior vertex without a leaf adjacent to it. Now, for lemma 5, if d plus k is equal to j1 plus j2, then d plus k is strictly less than the independence number. So let A be the set of leaves, which is an independent set. We know by the previous lemma that there must be an interior vertex that is not adjacent to a leaf. Call it X. Thus, A union X is an independent set. And since by lemma 3, L is equal to d plus k, we have that the independence number is greater than or equal to the cardinality of the union of A and X, which is equal to L plus 1 since we defined A to be the number of leaves, and plus 1 because we're adding X, which is greater than d plus k. Continuing for the proof of case 1, we want to create a new tree T prime with maximum degree d plus k, j1 plus j2 vertices of degree 2, and d plus k leaves. So for an example of this, if we're looking at this tree, this original tree with degree sequence, T prime degree sequence is going to look like this. So we've taken the excess from J1 and added them to J2, added them to the maximum degree. So if you were to compute the residue of the T degree sequence is 9, and the residue of T prime is 11. So it holds that the residue of T prime is greater than the residue of T. And so by lemma 1, we know that the degree sequence of T prime majorizes the degree sequence of T. Therefore, the residue of T prime is greater than or equal to the residue of T, which we saw in the previous example. It's easy to compute the residue of T prime is equal to d plus k, since we know that d plus k is equal to j1 plus j2. So by lemma 5, the residue of T is less than or equal to the residue of T prime, which is equal to d plus k and less than the independence number. So you may notice in this case, there are no cases of equality where the residue is equal to alpha, but in our other two cases, cases 2 and 3, we do have several examples where this holds true. We're not going to prove those in this presentation, but if you'd like to see them, they are in the paper. So finally, I do want to thank Dr. Jedek and Dr. Koshkin for allowing me to find my love for math over the last 5 years and sitting on my committee, and Dr. Waller for being patient with me and advising me on this project over the last 2 semesters. And finally, Dr. London for also being really patient with me through this, this crazy last semester. And so thank you for watching.